is being recorded in case you want to get back to this. All right, so for the first announcement, in terms of the test one grading, given that there were two sections and this particular term I had the biggest classes of my 5 to 6 years here, I was able to grade the first section completely, and for your section, I graded all of problem 1, but I was also able to grade some of problem 2. So give me a little bit more time. I normally take about a week to do that, but I acted faster this time, just given the class size. So far, good news. We did have a few complete scores. So well done. So God willing, I'll be able to finish, and next class I will turn in your tests. So that would be about test 1 grading. So for for going forward, we want to switch to a new topic and just call it simply leg 2, because the content will be mostly exclusive. So the test will be exclusive primarily. Of course, we still need to know contents from what we learned from chapters 1 through 3. Now we want to turn our attention to the next 3 chapters, chapters 4 through 6, and we want to talk about bending. All right, so let me switch to notes. So we have 2 theory slides for this chapter, again from the textbook, but I compiled them in one slide here. We'll go over this with examples as before to just make sure that everybody is on the same page. I'll take attendance just a few minutes. I just want to give everybody more time given the situation. All right, so bending. So suppose this beam, let me switch to red, it might be easier to see, is bent with this moment. So M in this course, let's take it as moment. It's bent upward, and this basically means that this opposite direction M means that, like what we did previously, that means it's fixed. But the textbook decided to expose the reaction moment on the other end. So this is the same as that. So if we bend this component, what happens? First of all, we see that this moment is curling about this Z. So really, M in this particular case is about Z. So I give that subscript for that reason. Guys, by the way, could you please confirm if you can see this good enough? Is everything readable, or I should make some changes? Jacob, thank you. Thank you, Drew. Appreciate it. All right. So what happens when we bend this? We bend this upward. It turns out that it follows this circular shape. So this segment that you see, it seems you're not able to see the cursor moving, but I'm referring to this shape. It turns out that it becomes a sector of a circular curve with the radius rho that is shown there. So rho, the Greek letter rho, is the radius of curvature. Yes, in physics you learn the rho to be density, maybe the same in chemistry or chemical engineering, but in this particular course we're referring this as radius of curvature. All right, so what do we know? From calculus, mathematicians proved that this equation holds between these parameters. Rho, again, is this radius of curvature they showed here on the shape, and M is the moment. E and I, 2 more parameters involved, but E is not new to us. So I'll take volunteers, first come, first served. Open question, guys. What are the names of E. Just give me one and I'll give you a point. Yeah, just say a point. Next time you're welcome to just raise your hand and then speak. Maybe it might be easier. Josiah Jacob, a point. Yeah, Jesus, what do you mean elasticity? Something else, right? Young's modulus of elasticity. Jesus, you want to correct that? You're welcome to do that. Elastic modulus, Evan, yes. So let me first give these people a point. Josiah, Jacob, Evan Mushler. All right. So yes, Young's modulus, modulus of elasticity or elastic modulus, or stiffness. It's also another name, stiffness. But I is a new name for us. As a prelude to that, anybody recalls the name of the parameter J? Raise your hand and then you're welcome to take the microphone. Yes, please go for that. Reagan. Reagan, maybe you muted yourself in case you're talking. Yeah, you're good now. Reagan, I cannot hear you. You're welcome to type it. All right, maybe she cannot hear me. Somebody else? Moment of area. Reagan, not completely, right? Anybody else? It was longer than that. Go for it, please. Evan?
Second polar moment of area.
Yes. Reagan, please correct your notes. Second polar moment of area. That second polar actually have mathematical meanings. That second means that square term that you had in integral, and polar means really what is different from the I that I want to go over. And then another question, what was the geometrical meaning of it? Again, I'm referring to J. Yes, please. Wasi.
Is it resistivity to torsion?
Yes, a measure of resistance to torsion. So really I is relevant to that. What's your point? I is, instead of second polar, take out that polar, second moment of area. So if you just take out polar, it becomes a new parameter, and that's I. This time it's a measure of resistance to bending. All right, and we have two geometries that we want to focus on. And this one is this, rectangular, and the other one is circular. And I, in general, would be calculated like this. Remember that J was integral of r squared dA, but this is y squared dA. And for circular, I is given as this. For a circle, J basically is IY plus IZ, because this was pi halves r to the fourth, and I, y, and I z are equal. Each one are half of J pi fourth r to the fourth, just for a circle. All right. So This gives us a measure of this radius of curvature, but what about stress? Stress is this equation from this point on. If I ask you what is the normal stress equation due to bending, simply say plus minus mc over I. Let's just look at this. The textbook refers to y in this particular case. What if what if the coordinate system is picked differently? Then it's different. To make it easier, let's just simply call it plus minus mc over I. So m still is the moment. C is a parameter that I want to go over maybe later. I is the second moment of area. So to be able to really understand these stress terms, we really need to know I calculation first. So let's go over a series of I calculations, and we should expect that to be mostly mathematical. Let's master them, and then we get back to the theory slide to really have our engineering discussion. So some of you whomever wants to write these down, you're welcome to do that now while I take attendance. I may do that again, just make sure that everybody is in, not just logged in and left. You're welcome to responsibly by typing in chat or responding in through microphone. Audrey. Audrey is absent. All right. Braden. Very good. Paul Arden. Very good. Olivia. Are absent. Jacob Dozama. Very good. Jack Fedul. Very good. Gray Ekman. Very good. Ethan Jackson. Ethan is absent. AJ. Thank you, AJ. Sander. Sander present. Olivia, again, I'd be checking again. Please be mindful. I'll put present for you. Sander, yes, I put present for you, Sander. Josiah.
Here.
All right, Audrey, next time, if I do not hear you responding, then I assume that you're not present, physically present. Audrey, I'll put present this time for you. All right, Josiah present. Tyler. Tyler, I know he's excused. Dylan. All right, very good. Wasi. Very good. Drew Linema. Very good. Justin. Very good. Reagan. Very good. Sturdy. Sturdy present. Kiro. Very good. Jesus.
Here.
Very good. Evan. Very good. Aidan. Good. Nick Reese. Very good. Nathan Schaffner. All right, absent. Jansen. Very good. Nathan Smith. Good. Leo Sobek. Good. Gabe Twiss. Good. Pax. Pax is absent. All right, so far you see Pax is absent, Nathan Schaffner absent, Ethan Jackson absent, and that's it. All right, so we said let's go over just I calculation, and you should expect that to be purely mathematical. So it makes sense to do that once for different geometries, learn it, and then really switch to our common sense engineering discussions. All right, so we said I is second moment of area. And when we say that, it's always defined with respect to an axis, because it really matters which axis you bend about. Sometimes materials are thicker with respect to an axis, so then that measure should change. And we said I is a measure of resistance to bending. So for this geometry, rectangular, we said if we go over the theory slide, or one of these equations, I suggest you do not really memorize it this way, because in 3D geometries, and depending on which one you pick as B or H, then it might be a little bit tricky, and especially during the test, it might be stressful. So instead, memorize it this way. And if you really simply follow the instructions as we do in class, it should be really straightforward. So do it this way, please. For rectangular geometries, do 1/12 base times height, one of them cubed. That one will define once we're done with plugging in values. So without any particular order, let's say base and height for now, put the values in. Cent is 10 to negative 2. So cube the one that is perpendicular to the axis. It's about y. Whichever side is perpendicular to y. It's this one. So cube that one. That's IY. And you know that in class, we normally get to do this together, and I'll look at your work and I'll give you points, but it's not efficient in virtually. So bear with me until we get to see each other next time, God willing, in class. All right, 5.12 times 10 to negative 10 meter to the fourth. So like J, I has the same unit, so meter to the fourth. So in engineering, as we went over previously, we tend to do a lot of unit conversions, and the idea is to give each other easy time, not hard time, because really dealing with such a small number is not as easy as really having an easier number without this 10 to negative 10, for instance. So suppose I want to convert this to centimeter to the fourth. Any opinion? How would you do that? I mean, we practiced this before, but any opinion? Yes, please. Drew. Drew, are you muted?
I apologize. Was my audio not working?
No worries. Now I can hear you.
Oh, sorry. The solution to that would be you'd multiply by 10 to the third.
I guess I said centimeter to the fourth.
Right. Oh, so that would be 10 to the negative third. I apologize.
Centimeter, not milli, right?
Well, yes.
Okay. So I see Olivia gave that response also. Any other opinion?
My God, why did I can't hear. I can't hear. I'll just.
Is it Drew? Drew, could you please mute yourself. All right, so as you guess, when you want a particular intensifier like centi, you divide by centi, right? But there's one little catch, centimeter to the fourth. So you should divide by centi to the fourth. So it should be 5.12 times 10 to negative 12, 10. 10 to negative 2 is centi, right? But because it's centimeter to the fourth, you have to divide by 10 to negative 8. So it's really 5.12 times 10 to negative 8 centimeter to the fourth. When in engineering, you see centimeter to the fourth like this, that basically means all centimeter to the fourth. So that was just one catch I want you to be aware of, not to put anybody on the slide, on the spot. All right, so that's in centimeter to the fourth. If I want us to be in millimeter to the fourth, then you would do negative 3 to the fourth. So radius 512 millimeter to the fourth. 10 to 12 comes up in the numerator. 10 to negative 10 cancels out. 100 remains, or 10 to 2 remains, and becomes 512. So really, by converting this to millimeter to the fourth, you're able to easily communicate this to other people. So be mindful of it. Again, who is saying what depends on the unit that that person uses. Different tables, different standards that you see in engineering, all should have units defined there. So be mindful of it. All right, so that's the first one. But as in the test or homework, I'll always be specific what unit I'm interested in, so that everybody gives me basically unique and relevant response. All right, so this IY calculation for this gives me a measure of bending about the y-axis. Now let's compare this with the right one. If we switch to the z-axis, if we do this, what changes? We said 1/12 base, height, one of them cubed. So let's stay with the base and height as before. We said the one that is perpendicular to z should be cubed. So z is this direction, so 1.2 is perpendicular to that. So cube that one. So if you stay with the same format, base and height, so then we see that we cube the first one, but in the second one we have to cube the other one. All right, so this is 1.2 times 10 to negative 9 meter to the fourth. So by comparing these two values, this one and this one, we see that IZ is bigger than IY, which means it's harder to bend about Z than Y. So that's why in buildings, in constructions, they use beams. If I put again, my drawing is not the best, but if this is our building, then they put the beams like this, so that the longer side is perpendicular to the Z, so that IZ gives maximum resistance to bending. So that's why you would see the beams oriented this way rather than on the flat side. So be mindful of that. Even though bridges are mostly flat when we walk on them, we want that to be mostly flat, the longer side, the thickness is less, but the beams that go into the cross section are actually oriented this way. All right, so that's the reasoning behind it. It gives maximum resistance to bending. Before I move on to the next one, guys, any questions for me? In fact, whenever you have questions, just raise your hand and ask that, so that I help you with that. All right, if no questions, let's move on. So sometimes the bending comes from an off-center load. Suppose there is an object like this. The load is here, and you want to see the effect on this cross section. And you see that really is this offset there. So how do we deal with that? Then we need to know this parallel axis theorem. Yes, you're getting exposed to this in this particular course, but later in fluid mechanics, or in machine design, you also need to know how to use this theorem, or even I calculation. All right, so what would you do? So this one and this one, we said we know that these are unique to these particular geometries, but this is the general formula. But if there is an offset like this, suppose this is y and this is y prime. If you know I about this y, what is I prime? This is the equation that you would do. You add this offset squared to area. So in this particular case, dy is the offset with respect to y-axis. It's not the diameter. Just defined this way in this theorem. So you offset, if you know the offset, square it, times the area of that object, even though the previous equations were not general, but parallel axis theorem is general geometry. It could work for rectangular, circular, or any other geometry. So let's do that. We go back in here, Iy prime, we said Iy plus d squared simply times area, no subscript there at all. But d is the offset. So Iy is the one that we already found in meter to the fourth in here. So 5.12 times 10 to the negative 10. Offset is given to be the distance between y and y prime, 7.7 centi, we know is 10 to negative 2 squared, and area of this object is base times height. You don't have to collect these numbers from the geometry again. Just look at what you put for I. So base and height are already given there. All right. So longer calculation. So this is 5.2 times 10 to negative 9 meter to the fourth. As you apply eccentricity, this off-center, it's called eccentric or eccentricity. As you apply eccentricity, then the value of I keeps increasing, and it makes sense because this value is always positive. And you keep adding that to the original I value, so it keeps bigger, bigger, bigger. So really I prime is greater than equal to Iy. They're equal when there's no offset, but Iy prime is always greater than Iy if the offset is non-zero. So that was for y-axis. Again, if you have any questions, please ask. All right, given that everything is recorded, I can have a faster pace. You're welcome to switch back to here and then watch the video. All right, Iz prime, the same as the previous one, Iz plus d squared area. Iz is the one that we already found up there, this value. Offset is 0.5 this time, squared times area, 0.8 times 10 to negative 2, 1.2 times 10 to negative 2. And this is 3.6 times 10 to negative 9. All right, again, any questions, just please let me know. All right, so we did all of this for rectangular geometry. If no questions, let me move on to the next examples. I want to really give you a complete list of what we would end up needing for this course all at once. And then we'll switch to engineering discussion as I mentioned earlier. All right, we just did I calculation for solid rectangular geometries. Now we have a cavity inside. Any idea, guys? Yes, please. Drew.
And then working with that one would be to take the area of the entire rectangle and then subtract the area of subtract the IY value of the hollow portion in order to find IY.
Very good, Drew. A point to you. Indeed, so as the equation suggests, so Iy prime of the entire thing is Iy prime of outer minus Iy prime of inner. So for the outer, we learned that is Iy plus the squared area of the outer. The same thing for the inner. All right. So for the outer, that means just focus on the outer rectangle. We did it in here. Just look here. We did it in here. Yes, dimensions changed, but the procedure is the same. So do not get misguided by that cavity inside. Just look at the outside. So we said 1/12 base and height of the outer, cube one of them, and then square the offset, and then times the area. So the area elements would be really here and here. You put them there. So base and height of the outer 1 centimeter by 1.4. I put that. We said we cube the one that is perpendicular to y. So y is in this direction. Perpendicular to that is this. So really 1 centimeter should be 1 centimeter should be cubed. All right. So that area we also put these elements in here. The offset is remaining. The offset is given here as 0.6 centi. So all of this is for the outer. All right, we repeat this, put all in brackets so that we're subtracting all of it, not just some of it. So we repeat this. Now the focus is just on the inside. A new rectangle, new dimensions, but the same idea. So 1/12 base and height, offset squared, and these elements should go in here and here. So base and height, if I retain the same order base and height that I picked in here and here, then this should be cubed. I can confirm that once I put the numbers also. So 0.1 is the thickness that should be subtracted from the two sides. So 1 minus 2 times 0.1 is 0.8. And the height of it, the same thing. 0.2 should be subtracted by 1.4, 1.2. And I put these numbers immediately here. And let's confirm this cubic. So we said perpendicular to y, and that should be this direction. So it's 0.8. Indeed, that should be cubed. And the offset remains at 0.6 centimeters. Longer calculation. So for us to do a little bit work, I don't want people to get to sleep. So how about we do this? Give me this value, and it's about trust. Please do this. and then put it in the chat, and then I'll give you a point for that if it's correct. Or I do this. Simply I do this. I put the number in. Again, it's about trust. I do this for you guys. I want you to learn it. Then you put the number, and then if you found this to be correct, say so in the chat. 2.2 times 10 to negative 9 meter to the fourth. Just say it in the chat so that I am giving everybody and not missing anyone. I understand it needs a little bit of time, so take your time. All right, no problem. So let's move on to the next one. We're just switching to circles, but ideas remain the same. So I prime, IY plus D squared area, but D is not diameter, that's offset. So make sure you make note of that. An area for a circle, we know that is pi r squared. All right, IY, if we go back to the theory slide, we said it's pi fourth r to the fourth. So pi fourth radius to the fourth. And radius, we see that's 1.2 times 10 to negative 2, because that's in centimeters. The offset is 2.5 centi squared times area pi r again, as given in here, squared. All right, IY prime 2.99 times 10 to negative 7 meter to the fourth. All right, so that was for one circle. Now if it's hollow, as Drew said, we do the same thing for this one. You just do outer minus inner. So IZ plus D squared area of outer, IZ plus D squared area of the inner. So for the outer, just focus on the outer circle. Pi fourth radius to the fourth, 1.2 times 10 to negative 2. Diameter again is not the D is not the diameter, it's the offset in this case. So it is 1.5, 1.7 square it times the area. So pi r squared, again r is given in here. 1.2 times 10 to negative 2 pi r squared. So plus, that was all for outer. We want to switch to inner. So pi fourth r to the fourth for the inner, plus offset squared pi the radius squared. So the radius of the inner 0.4 is the thickness. So really I'm looking at this, which is 0.8. I put that also in here. And the offset still as 1.7. By the way, this is all subtracted. So we should subtract all of it. All right, and this one gives us 8.57 times 10 to negative 8 meter to the fourth. If I want to convert it to centimeter to the fourth, we know that you have to divide by centi to the fourth, which is 10 to negative 2 to the fourth, which is 10 to negative 8. So really it becomes much easier. Centimeter to the fourth. All right, I have the least interaction in this particular section compared to the first one. I assume that everybody is listening carefully. All right, so that's what we did for these two geometries. I want to do one more geometry, and that would be the last example. But basically, two examples, one geometry, which is the T shape, but about the two axes. So the first one, about y for this, appears to be the easier of the two. And the second one appears to be the hardest among all of the ones that we did so far. And that would be really the extent that we would go over in this course. All right, so there are two pieces. So it makes sense we have to add them one at a time. So suppose this is 1 and this is 2. So I about y, then we need really iy, because if we look at the upper piece, the centroid is somewhere here in the middle of that segment. And the bottom piece is right in the middle. So if I put maybe a different color, if I put y-axis here, if I call it y1, and if I call this y2, I see that y1, y2, and y are all coincident. So no offset. That means d equals 0. It just makes it easy for me now. Really, then this is iy for the piece 1 and iy for the piece 2. No offset at all. All right, now focus on the upper piece. We said it's rectangular, and we said it's 1/12 base times height, one of them cubed. So base is 90, height is 20. Which one is cubed? We said the one that is perpendicular to the y-axis. So y is this, perpendicular to that is 90, so cube that one. We do the same thing for the lower piece. So 30 by 40. All right, because I went with the same order, I know that the first one should be cubed, but let's confirm that. So we said the one that is perpendicular to y is in this direction, so this side should be cubed, which is 30. So cube that one. So this is the I about that axis, 1.31 times 10 to -6 meter to the fourth. All right, guys, any questions? Please let me know. All right, good. So let's redo this problem with changing the axis. Let's solve for IZ this time. Remember that center is in here for the upper piece. We call this number 1. We call this number 2. And for the lower one, the center is in here. So if you want to know Z1, then really Z1 is here, Z2 is in here. So the offsets, remember that they're between the overall Z, this is D1, and the axis going through the centroid of that object. So this is D2. We need to know D1 and D2 values so that we can calculate our I. So remember, IZ equals I Z1 plus, let me actually do this easily, D squared area for 1, improve this, D squared, and IZ plus D squared area for number 2. So then really we need to know the offsets. IZ would be just cubing a different term compared to what we did in the previous example. So to do this, then we have to resort to what we learned in statics. So centroid calculation. So we really want to know where the z-axis is residing. So C, let's call it the overall centroid. So we learned in statics, the first item is pick coordinate system. So let's put that coordinate system, for instance, in here on the bottom left corner. Whatever you picked, that's absolutely fine. Just stay with that, and your calculation will be with respect to that point. All right, so that's the coordinate system. So overall, let's call this, because this is in the direction of y, we are after y bar. So fill up the table. What is that? It's this table. You have two objects in this case. Put them the first column like this. You are after y bar, so put y bar I, and then area I, and I takes values 1 and 2. There are two objects. And given everything is in millimeter, put the unit by the parameter. We know that for area is millimeter squared. All right, so y bar I basically means this. with respect to the yellow coordinate system that we put there, volunteer, give me the y value of the centroid of piece 1. Cole, with respect to the yellow coordinate system, right? You're almost there. Look at the upper piece. The centroid is somewhere in here, right? 50, Jacob. Yes, Jacob is correct. Jacob a point. So that's why we picked this coordinate system. Everything is with respect to that. So 10 is this little, half of the 20, and then 40 should be added. So it becomes 50. And I put the unit up in here so that I do not repeat it with the number. All right. An area is the area of that piece. And it is 20 by 90. So, or 90 by 20 if we always go with base times height. So 1800 millimeters squared. We repeat this for the bottom one. So somebody please help me with y bar 2 now. How far? Or the distance between 2020 all at the same time. Kiro and Drew a point. All right, so yes, it is this length. It's y bar 1. So that is 20. And the area is 30 by 40. All right, then y bar, the third step, the overall y bar, this one that we are after, is through this formula, y bar 1 a1 plus y bar 2 a2 divided by a1 plus a2. Had we had more than two pieces, just keep adding to the numerator and denominator accordingly. So in this case, all right, in this case, would be 50 times 1800 plus 20 times 1200 divided by the summation of the two areas. So this gives me 38. The unit is in millimeter. We went with milli everywhere. So that is in millimeters. So really this, from this point on, is 38 millimeters. Now, once we pick this, we're able to fill up D1 and D2. So I want to volunteer for D1 and another volunteer for D2. Look at the geometry. From the bottom point to C is all 38. What is the distance? D1 as shown, or D2 as shown. D1. Again, look at the D1 length that I defined in the figure, Kiro. Look at point C. Yes, Drew was yes, that's correct. Look at D1 is this length. So 2 plus 10 is 12. So Drew was all right, 12. What D2, guys? Evan Drew, correct. All right, that is indeed 18. Again, this much is half of 40, which is 20, and all of from the bottom to point C is 38, so 18 remains, which is D2. All right, with those said or calculated, let's do this. IZ of upper piece is 112 base times height, one of them cubed. D1 we found that to be 12. D squared times area of the upper piece, base times height, and we know that if we know these values, these go also in here. Repeated for the bottom piece, base and height. 18 is D2, base and height. So base and height of the upper piece are 90 and 20. So put them here. Base and area of the lower piece are 30 and 40. We have to just cube one of them. So we said the one that is perpendicular to Z should be cubed. So look, if this is Z, perpendicular to that would be this direction, which would be either 20 or 40. So cube 20 and 40. And given that today you're not very fond of calculation, I'll give you the number to you. All right, that is 8.68 times 10 to negative 7 meter to the fourth. And if you want to convert it to centimeter to the fourth, you divide by 10 to negative 8. So it becomes 68.8 centimeter to the fourth. All right, so as expected, this is more involved than other problems that we did. So if the shape is irregular and centroid should be calculated, so it really requires more work. So in SolidWorks, if you have used that, normally when you devise your geometry there, it has really options to easily give you the centroid location or other parameters, also I or J as needed. All right, guys, any questions for me? Yes, please.
Can you explain how you're finding D1? I can understand D2, but I couldn't figure out D1.
No worries. So do you see the point C that I marked there?
Yes.
All right. And you see that point is 38 millimeters from the bottom face. You see that?
Yes.
We call it Y bar. All right. And look at the location of Z1, the centroid of the upper piece. It's 10 millimeters from either top face or bottom face of that upper component. You see that?
Mm-hmm.
But do you see the D1 that I marked there is from that upper mark, that the centroid to point C. So 10 is the upper component, and from the bottom of upper component to point C, there's 2 millimeter that you had mentioned. So 10 plus 2, 10 plus 2, yeah, this is 10, and this little thing is 2.
Thank you.
Are we good now?
Yes.
Kiro, by the way, Meshraki, does it happen to mean anything related to East?
I do not know. I just know it's Egyptian family name. That's
I
all I
see.
really got.
Yeah. It's not exactly the same, but in Persian we have a word mashriqi. Some people they don't have it. They say mashriqi like that. I was just wondering whether it's that, but
Yeah.
no problem. You're still my friend. All right. If no question, guys, I suggest we take the break now, and then once we come back, we'll continue. So please come back by 11:25, and I'll be muting myself. Make sure you come on time because I'll be taking another attendance. All right, welcome back, everybody. All right, I'll be taking another attendance just shortly, but I want to give a few more minutes. All right, so let's see what we did. So we started talking about bending. We said when we apply moment to the object, it bends like a circle, and radius of curvature rho will be found through the equation given. Rho equals EI over M. But in the textbook, it gives it in the inverse form just because later we'll be adding another equation to the right side of it. All right, so we said I requires all those calculations, and through several examples, we learned how to do that. Now, let's switch to our engineering discussion, how to calculate the resulting stress. When there is pure bending like this, only moment is applied, we said sigma equals plus minus mc over I. So as opposed to axial loading, when you apply a force to an object axially, we said normal stress sigma equals F over area. It could be positive if you're pulling, it could be negative if you're pushing. But the stress will always retain its value. It will be positive all the time, or negative all the time, or zero if there's no force. Otherwise, it never switches from one value to another one at different locations when you're talking about average values. All right, but here in bending is different. If we're talking about different points, then it could be any of the three possibilities. It could be zero, it could be positive or negative. So how? So for this particular case, we said we're bending it upward. So as shown in here, this upper piece, it gets shrunk or shortened or wrinkled. So on this face, stress is negative. In contrast, in the opposite face, it gets elongated. That's the only way that geometry would allow this deformation. So one side is negative, the other side is positive. So depending on the location of the point, then you pick the sign accordingly. So the textbook says the sign is the product of two signs, one for M, one for C, but I think it's really complicated. After teaching it for about 6 years, I think it's easy to really geometrically figure that out like this. You bend it upward, visualize the deformation. If it shrinks or gets jammed or wrinkled, simply say it's compression, it's negative. Shortening is negative. If you're pulling, then it's positive. All right. So if on one face you have negative and on the other face is positive, then because of continuity of the material on the cross section, there should be a fiber in the cross section that remains inextensible. So it's called neutral axis. So somewhere in here, this fiber, this neutral axis is given in here. So on this face, there's no stress. Really, there's no strain or there's no deformation delta. It remains inextensible. Slightly above is negative, slightly below is positive. And of course, if I reverse the load from counterclockwise here to clockwise, then everything reverses. All right. So we learned the sign, we learned I calculation, we learned M, and in fact, remember, M and I get the same subscript. If the bending is about Z, M and I get the same subscript. What about C? let me go over this quickly, and then I want to do some examples and then get back to this theory slide. Make sure that everybody's on the same page. C, let me put it in here. C is the perpendicular. Make sure you do put it in your equation sheet. In tests, I've seen people making mistake on finding the C value, in particular if it's 3D or giving you a perspective that doesn't look just 2D. All right, perpendicular distance between neutral axis or bending axis and point of interest. What does that mean? If I want to calculate the normal stress on this face, if the neutral axis is this, the C would be this value, the perpendicular distance between the two. If I want to know what is the stress on the bottom face, simply this is the C value. If I want to know, or I want to calculate or confirm the stress, the neutral axis is 0, then we know that the C on this is how far you get away from this, which would be 0. So C would be 0, therefore stress there would be 0. All right, we also said, let's calculate or go over the first example and calculate some terms that we learned today. Some of you might have the habit of writing down things, even online, so I'll give you time. But meanwhile, I can ask this open question to everybody. Where would you find applicability for bending in practice? Just name it, please, one at a time so that everybody gets a fair chance. Raise your hand and respond like that. It's just easier. Yeah, the microphone, please. Jacob, please.
In bridges.
Bridges, yes, a point to you. Yes, leave your hand up until I give you a point. Brayden, please.
Would a skyscraper be an example?
And the load comes from?
The wind.
Yes, the side. Yes, a point to you. Yeah, please leave it down. Gabe, please.
Let's see. Semi-truck flatbed trailers.
Very good indeed. Justin, please.
Like a vehicle car frame.
Rim. The load comes from radially, right?
Sorry, you cut out a little bit. What'd you say?
Yeah, the load comes in radially, right? Because the rim, I don't know what we call them, the limbs are not exactly vertical. They're a little bit slanted. So the load comes in a little bit radially. Yes, I gave you the point, Justin. Jacob, you will not get an extra point, but go for another example.
No, I thought you wanted me to keep it up for the point.
Oh, no, I did give you, Jacob. Yes, thank
Okay,
you for that. I did give you. Kiro, please.
Simply like a couch when somebody sits down on the couch.
Very good indeed. Drew, please.
An example of being a crane arm lifting a load from one position to another.
Correct, Drew. A point to you. Jesus, please.
I was thinking like a tire when we fill it up, it bend in there. Squeeze it? It squishes it? I don't think so.
Yes, it does.
Oh.
It does. It flexes. Yes, Jesus.
Okay.
Wasi, please.
Would a diving board be a proper example?
Yes, but not in this season, right?
Yeah.
Yeah, thank you very much. Yes, Jesus Wazi, please put your hands down. So window sill, for instance, if you want to go to other dimensions, yes, all the walls, the side winds that we get, the electric poles, all the winds, all the load-bearing components that are relatively long, balconies, overhanging pieces, let's say in learning commons. I had student always related applications to learning commons. Jesus, you have a question? Your hand is up.
No, sorry, I forgot to take it down.
Oh, no worries. All right. So given all these examples, really we find bending to be ubiquitous. So what we want to do, remember, our goal is to be able to comment on mechanical safety of these components in those applications that we went over. So then we have to be able to quantify stress. In bending, two stress types occur. One of them is normal, the other one is shear stress due to bending that we'll go over later. So let's calculate stresses. So 3 points, A, B, and C. So we said plus minus MC over I plus minus MC over I for A, B, C, and then rho, we said EI over M. So we see that M is bending or curling around Z. That's how I determine the bending axis. So it's about Z. So really this M is about Z, and M and I get the same subscript everywhere. And C goes with the point. So it's point A, B, C. Now we have to figure out the signs. And that is something that we do by visualization. So engineers tend to have good visualization. So let's practice that. So I need 3 volunteers basically to tell me what sign to pick for the points. Just visualize, bend them upward, and then see whether that side, the point on that side is basically wrinkling or elongating. Guys, believe in yourself. If you think it's easy, still go for it. Bend it upward. What do you think? Top face, A resides on it. Kiro, please.
So, am I following like if M was being pushed downwards, or if I'm like pushing up, as in the same way, like
Yeah.
be pushing upwards?
If this is Z, M is upward, like that.
Gotcha. So then
Yeah.
I think A would be negative because the top part would be in compression.
Correct. Then you made it easy, Kiro. Then C would be opposite. What about B? Actually, any other opinion? Everybody, Kiro, a point. Evan, please.
Is it on the neutral axis?
Indeed, a point to you. It's right in the middle due to symmetry. Evan, a point due to symmetry. Really, it's zero. It's neither positive nor negative, and that zero shows up in the parameter C. So let's calculate them. So first IZ, because it's recurring, calculate it once. It's rectangular geometry. Look at this cross section. 1/12 base times height, one of them cubed. So it's 12 by 20. Let me switch to that slide of my notes. All right, this is 8.8 times 10 to negative 9 meter to the fourth. All right, given that it's repeated, let's do in parallel. That's 60, 8 times 10 to negative 9. This one is, we don't know the sign on that yet. All right, so we have these. So for C, if you go with the formula, again, instruction, just write it down. It's human nature to forget things, but please write it down. That was one of the nemesis that I've seen people in the task make mistakes. All right, so we said if this is the axis Z, bending is about Z, put these arrows. You're measuring C perpendicular to that direction, from that to the point. So from that to point A is half of 20, is 10. For C, go downward, but still in that direction, the same value. But for B, there's no distance if you go perpendicular direction. So that's 0. So really that's 0. Again, if you put these arrows, then you know that you have to measure in that direction. You do not go away from that to get to point B. If you slide, yes, you get different value, but you're not sliding. You're going in a perpendicular direction. All right, so this is negative 75 megapascal, and this is 75 megapascal. So we found these values. One way to present them pictorially is this. If we view in this direction, then point A is here, point C is in here. What we do, we say on A, we see that it's negative. So we push that point inside with 75 megapascal. For C, we pull it out, the same amount. And then we connect these two. And this point should be the center point B. It should not have any value, it should be 0. The further away you get from the vertical line, the more the stress. So all of it is positive here, it's negative here, and 0 here. So this is called stress profile. And this is what we had in the theory slide, if you saw that in the textbook in here. Basically saying that the top piece, as we said, is negative. It is negative, pushing in. The bottom face is all positive, as we did it in here. And here we have 0 because it doesn't have any distance from this. That's called stress profile. All right, let me switch back to example. All right, so we have this, and then rho, just calculate this. 200 times 10 to 9 is E value, and I, again, I and M get the same subscript, all about Z. 8 times 10 to negative 9, and M about Z, not M, is 60. So rho is 26.67 meters. What this means is really it bends like a circle upward, and from the centroid, really this is the rho that we calculated. That's all that. So I'll give you time to digest this or write it down, and let me take another attendance. Audrey, you're welcome to just simply type in chat. It's just easier for me. Audrey, good. Braden, thank you. Cole Arden, Thank you. Olivia. Thank you. Jacob Dozama. Thank you. Jack Fedul. All right, then I put absent for the second half. Gray Heckman. Thank you. Ethan Jackson. Ethan, you're in, so you were not in for the first half per my attendance. All right, put present for you for the second half. All right, AJ. Thank you. Sander Nis. Thank you, Sander. Josiah. Thank you. Tyler Leschuk. Okay, he's excused. Dylan Limoges. Thank you. Wasi. Thank you. Drew. Thank you. Justin. Thank you. Reagan. Thank you. Sturdy. Thank you. Kiro. Thank you. Jesus. Jesus is all right, absent. Evan Mushler. Thank you. Aidan. Thank you. Nick Reese. Thank you. Nathan Schaffner. All right, still absent. Jansen. Thank you. Nathan Smith. Thank you. Leah Subek. Thank you. Gabe Twist. Thank you. Pax. All right, still absent. Oh, Pax is here. Okay, you're present for the second half per my attendance then. All right. So again, guys, please be mindful of it. I'm doing extra work. I'm taking attendance for the second time just to make sure that I'm being fair to everybody. All of you that put the time, you come in and you're attentive to class. Jesus, what was the issue?
I had to step out. I was talking to my mother.
All right. All right, I put Jack, I don't understand. What's the issue that you have, Jack? All right, put present for you. All right. So, by the way, before I forget, let me remind you that attendance is important in this course. You see the level of interaction that I have with you guys. You're allowed to have 2 unexcused absences. Otherwise, that would be a failure for the course. So please be mindful of it. All right, so what we did in this example, we calculated stresses at different points, and of course, radius of curvature. If material property is given to us, we're able to compare that with the stresses that we found, and then we can determine whether the object is safe at that point or not. We'll have examples like this in the future. All right, so now what I want to do, let's redo this example with changing the axis from Z to Y, and then let's see what the implications and changes are. All right, so the only thing that changed is the bending axis. We see that it's curling about y, so really it's about y. So we need IY calculation, sigma A, sigma B, sigma C, and rho. That was EI about M, but we know that's about Y this time. So plus minus, plus minus, plus minus, MC over I. Please remember this way, not the one that the textbook gives, MY over I, because Y would depend on the neutral, on the coordinate system that we pick. But MC over I is more general. All right, we said this is all about Y. And C goes with the point. So IY, again, still rectangular cross section, 1/12 base times height. One of them is cubed, 12 by 20. So I put that in. And one of them is cubed. We said the one that is perpendicular to the axis, perpendicular to Y, is 12. So cube that one. 2.88 times 10 to negative 9 meter to the fourth. You don't have to convert it to any other unit. Leave it as SI. That's the number that we need for stress calculations. All right. So we have to pick the signs. All right. I need volunteers, please. I need signs. Yes, please.
B would be in compression.
Evan, maybe you're muted.
B would be in compression.
Oh, yes, but yeah, I was not able to hear. B is in compression. Indeed, yes. Thank you, Evan. And also, Cole and Kira were confirming. Yeah, but unfortunately, I was not able to hear anything. All right, Evan, a point. So B indeed is in compression. Just visualization. You bend it to the right. If you do it with your hand, you will see that the inside, the palm of your hand would wrinkle, but the outer face is just being elongated. So on this face is negative, on this face everything is positive, but on this face and in the middle is zero, it's neutral axis. All right, then point A is positive, let's pick that as positive. Point C is positive on that same face, and B is negative. All right, so numbers, we have them, 60. IY, let's again, as before, let's just do in parallel, negative 60 times. All right. So CA, help me please. One volunteer, one value would give really all. CA, what would be the value for CA? Yes,
Is it 6
Braden?
or 6 millimeters?
Yeah, if you're talking, I don't know what happened.
Oh.
I'm not able to hear anything. Are you sure you're not muted? Oh, 6 millimeters. Yeah, Braden, Jacob, thank you. Yeah, I don't know what happened. I'm not able to hear anything. Braden, you said 6 millimeters. Indeed, that's correct. Yeah, let's then just simply type in. For some reason, the system does not like me now. All right, so yes, we said by instruction, really, once you figured out the neutral axis or bending axis, quickly put these two little arrows. Go in those directions for the C value. So A, B, C are all 6 millimeters away from neutral axis. So put them in. All right. So the values now are 125 megapascal. And it makes sense for A and C to have the same value. They are really the same distance away from y-axis. So they should be really undergoing the same stress. And because of symmetry, B and A should be really equal and opposite too. So really follows intuition. So if you view from the top, then this would be point B, and this would be A and C. So on B, we have negative, on A and C, we have positive, so connected to. So 125 megapascal. So again, this is stress profile. All of it is positive that you're pulling, and all of it is negative. So this is positive, this is negative, and this is 0 on the neutral axis. So if you compare this with the previous one, we had only 75 megapascal. When we had the axis loaded like this, but here we're getting 125 megapascal. So that was the reason I said in buildings you would get to see components oriented this way, and the load is coming either top or bottom like this. You're bending it upward, whether it goes up or down is the same thing. But if you lay your beam like this and you load it sideways, as if you're putting really the beam like this, and then you're loading it downward. So the better one is the first one because it gets less stressed. As an engineer, we should be mindful of that. That's the lesson. All right. So that's that, and then let's do row calculation. So nothing different, just some numbers changed. Particular I. And this is 9.6. So you bend that to the right, it bends on the same plane from the mid face. That's the row that we calculated, 9.6 meters. So that's that. I give you time if you have any questions on this. All right, if you don't ask questions, then I'll get to ask you guys questions. So I-beams, you may have seen beams, especially the steel beams, having a geometry like this, an eye. Anybody can comment on it? Why this would be useful at all? Yes, Braden. Yeah, oh, okay. The issue is I'm not hearing again. Braden, could you please type that? Or anybody else wants, just simply type, then at the same time it would be fine. It is reduced weight, but just because I want, okay, WASI, yeah, WASI. That's the reason, right? Same thickness, but with less material. Not just because it has the same thickness, because it has this almost the same strength, which WASI said more completely. So we learned that sigma equals MC over I. And no matter what the geometry is, we said this M remains the same. That's the load that we're applying. So by changing the geometry, we're changing the I value. The C remains the same at different location. We say at this location, what is sigma? At that location, what is sigma? So C is not changing. So the only thing that you're changing is the I value. So the more the I value, the less the sigma, because they're inversely proportional. Now, we learned that if we look at the I value in this case, for instance, the more the I value, so this component is being cubed. And we learned by stress here that at point B, actually in here, it's just more easier to follow. If we look here at B, we learned that there was no stress. Really, that was the load that we had. Suppose we're walking on it. We're walking on it. So this one is neutral axis. Sigma equals 0. The ones that are not non-zero and most significant are these two faces, equal and opposite, really critical locations. So that means we can take, if I switch to blue, we can take out the material like this, because really this 0 here, as we go up, it gets more. So take out majority of material from the middle and instead strengthen these two locations. So strengthen these two as needed, but not much is going really through the intermediate interior segments. So for this reason, people said, yeah, why not making it I shape? Take out the material. We are making it lightweight, but this is important, but almost with the same strength. Is it exactly the same? Of course not, because we're taking out materials. We are making it of a strength value of less than before. But some people, again, might add chemicals or strengthen these two segments, then it would be harder. But in general, if it's this geometry or the corresponding I shape without any chemical treatment, then this is stronger, but this might be really about 98% as strong. So really it makes sense to use the I shape. But keep in mind, we have to put it in this configuration. Now, so we said we do this assuming that the load is up or down. If it is sideways, we have to rotate it. What if the load is both sides? Then we put two of them like this, or we make it rectangular, hollow rectangular like this. Then we're handling both directions. It really depends on applications. And engineers are always like this. They look at the application. Depending on the situation, they give a solution. So that's why really we go over all these different examples to make sure that we have a good solution for every case. All right, guys, any questions for me? All right, so we'll have one homework for this leg basically for test 2. And I may post it sometime soon. And if I do, it will be on Sunday at midnight as usual. If I did not, I may post it the second next week, just because again, whenever I post it, I should give you about a week, and then it should be done before the test. So that's why we have a little bit room to work with. So that's about homework. Was the test to the schedule is given in Blackboard in the syllabus. Yeah, we'll quickly we'll closely follow that. Please take a look at that. But we'll always have a review session before that, so there should be time to really to do that. So no worries on that. All right. If no questions, I think it's best to leave it at this point because I want to be in sync with the first section. Once I finish up the grades, the grading for test 1, and I'm thinking of next class, I'll return the test. If no question, guys, thank you so much. Enjoy your time and see you hopefully in class and this coming Friday. Have a great rest of your day. Thank you, Gray. Thank you, Jacob, Drew, Kiro,
Thank you.
Olivia.
Have a good rest of
Thank
your
you. Thank you, everybody. Josiah, Nathan, Cole, thank you so much. Braden, thank you. Justin Pax, thank you.